Hello and welcome to this recording related to chapter 14 from our textbook. And I think we are in week 5, week 6. The topic for this and the next few sessions is frequency selective circuits. That's the name of the chapter in the textbook, chapter 14, and this is still the electric circuits textbook, Nielsen and Reader. So frequency selective circuits are also commonly called filter circuits, so I may be using both the names interchangeably, and I hope that doesn't confuse you. Okay. So we started our study of the frequency domain analysis last week, where we looked at some an introduction to certain ideas such as the frequency response based on the transfer function. We looked at the definition of a decibel and how it's used to quantify magnitude gain in terms of a logarithmic scale. We also studied the plotting, meaning making graphs of the frequency response, and we studied two different types of graphs. One both on semi-log scale. That means one of the axes, the x-axis, is logarithmic and the other axis is regular. And we studied the magnitude plots and the phase angle plots, and those we called board plots. So that was all of the material that we covered last time. So you can consider this chapter, chapter 14 in week 6, as a continuation of what we have studied last time. So as I start to define some of the new ideas here, you will discover that much of what I'm saying you do know in the past but because of having studied various other things. So I don't feel that there are significantly new concepts here, but definitely there is some new ways to look at old ideas. Okay. Alright, so having given you that introduction, let me skip to slide 2 on the PowerPoint, and my PowerPoint is called Chapter 14 Filter Circuits Lecture Notes PPT. So I hope everyone has it open and you're looking at slide number 2. So on slide number 2, we have 5 topics listed on the top, and then I have one more topic also listed on the bottom, but this is from the next chapter, chapter 15. So really speaking, our textbook has 2 chapters devoted to filter circuits, one chapter 14 and one chapter 15. Now chapter 15 is not too different, but is an extension of what you're going to study in 14. And generally in a first course, we don't have enough time or necessity to go too deeply into active filters. So I thought I'd at least introduce you to the idea. So I'll give you maybe just one section from that chapter 15 so that you are also exposed to those ideas of active filters. So regular filters and active filters, or passive filters and active filters, and everything we will study in chapter 14, you can actually call them passive filters, and chapter 15 is all about active. Now you'll soon understand what the difference is, but for now let's say we focus on passive filters in chapter 14, and maybe I'll have one quick look at what is in the first section of chapter 15, and we'll leave it at that. I'm sure at some point in your next course of study in next year or two you will run into a more detailed analysis of active filters. Okay, so of the 5 sections in chapter 14, we start with some preliminary stuff in section 1, and then the next 4 are about 4 different types of filter circuits. Okay, 2, 3, 4, 5 are the 4 sections, and so we start with low pass filters, high pass filters, band pass filters, and band reject or band stop filters. Okay, so that is the plan for the rest of this week, meaning 4 sessions at least of recordings. So let me move on to slide number 3. So here's a drawing that I picked up somewhere, and I hope this can help us illustrate or show to you the basic idea behind why filter circuits exist and what is the need to use them. Okay, so on this block diagram to the left you have something called an original signal or a complex signal. You can see that that complex signal has a number of magnitudes and a number of frequencies, etc. But that is, like what a real signal would be. Like, so let's say one of you began to sing a song. If you sang for 1 minute, or if you spoke for 1 minute, it's likely that the waveform that you record, if you manage to record whatever you're speaking into a microphone, and you record it in an electronic amp, you will find the signal looks somewhat like that, right? It's not a smooth sine wave, but it's a mix of many things. You may also remember in one of the last sessions, I introduced you to the idea of harmonics and something called a Fourier series. We are not studying Fourier series in this lesson in too much detail in this class 280, but I did tell you that any complex signal, which is not only one frequency or one amplitude or one phase, any complex signal can be shown to be a mix of many pure sine waves, sine signals, sine or cosine. Now they may be pure sine and cos, but they may have different amplitudes. So if you mix enough of these various frequencies together, then you can actually recreate the original signal. Okay, so that's what you see in the middle there, where it says component frequencies. What it's telling you is that that original signal, which has a number of frequencies and a number of amplitudes, can be thought of as having roughly 3 main components. Okay, there is the primary component, that is the lower frequency in large magnitude, and then generally it's called the fundamental component, and then the other 2 you can consider as harmonics or additional components, and if you add the all 3 together, ideally you get the original. Now generally speaking you need more than 3, but just for purposes of this particular diagram, let's just assume there's only 3. Okay, so you have a low frequency, high amplitude, and then you have a mid frequency, medium amplitude, and then you have a very high frequency but low amplitude. So you have 3 components. Okay, so let's say you put them into filters. Send the whole thing, all the combination of 3, into, let's say, a low pass filter on the top. So what happens is, on the input you have this complicated frequency, signal. On the output you get a nice only one signal, and that is the high amplitude low frequency signal. So only the low frequency component has come out to the output, and the rest have found such high impedance that the voltages, because of the other 2 components, the high frequency components, just don't appear on the output. So if you look at the output voltage signal and put an oscilloscope on the output terminals, all you will see is a neat recreation of only that low frequency component. Okay, so that is why that filter is a low pass filter. It only allows low frequencies to go through. The next filter, the second from the top, is a high frequency filter. So what is the high frequency filter doing? It's allowing only the highest frequency component out, and the rest of it is blocked. Then you have something in the middle or something below that called the band pass filter. And what the band pass does is it only allows frequencies in the middle range, not too high, not too low, but somewhere in the middle, to appear on the output. Similarly, the very last one is a band stop or a band reject, or also it's called a notch filter. And you see that it only blocks the center, but it allows the low and the high to come through. And if you look at the magnitude diagrams on the rightmost side, starting from the top, where we have the low pass filter, then we have the high pass, then in the mid band pass and the notch, you will notice that the diagram shows you in a graph what happens to all the frequencies that are put into the filter and what comes out. So you can see that the low frequency, low pass filter, for example, has a high magnitude, right? That flat line, which is the response of the circuit of the filter, it is flat, meaning whatever is inside comes out. Assuming let's say a gain of 1, whatever is coming in comes out, but only such parts of the input signal whose frequency is low, below that point where it starts to drop off. So everything with a frequency below that has a gain of 1, but high frequencies, which may still exist, which they are there right on the input, but they don't get a chance to go out. Okay, so that's the behavior of the low pass filter, and then you can see the others also. So we'll do more on these as we go through the remaining minutes of this lecture and the next few lectures, but I thought this was a good way for you to understand why we need filters and what the benefits are. Okay, all right, so moving on to the next slide, and this will be slide 4. Some more definitions, some more graphics, some more drawings, but I think you're starting to get the basic idea, right? So a definition of a filter, as you can see in the box there, is a circuit that is designed to pass signals with desired frequencies and reject or attenuate others. Attenuate is a term that you may use, so hopefully you may run into often, so try to remember it. Attenuate means reducing or decreasing the magnitude. Okay, so a filter can either totally reject, meaning nothing comes through, or it may reduce the effect of some frequencies, and many other frequencies which are desired, you want them to be there, those are allowed to pass through. Okay, so that's the basic definition. Try to understand the graphics, the drawings below. So I show you for the low pass filter, the high pass filter, the band pass and the band stop. There's a few more details that you see in each of these drawings now. It's not just a simple shape. Also, we show a very sharp square or triangular type response, right? So there is a fixed pass band, for example, on the leftmost filter, the low pass, and then at omega c, which is a certain frequency called the cutoff frequency or the corner frequency, boom, the magnitude of the gain just drops to 0 instantaneously. Okay, so that is how we show, and this is an ideal drawing, it's not a real drawing, but this is how it helps us to think about circuits, about filters. Okay, so that's for the low pass. Similarly, you see the phase angle drawing below. Now both these drawings in this chapter, for some reason the writer has chosen not to use board plots but just regular plots. So the magnitude is not in dB, not in decibel, but just ratio. And he uses board plots in the next chapter for active filters. But for now, you still get the point, which is that there is magnitude and there is phase angle, right? Both are necessary to talk about frequency response. And so the phase angle is the one on the bottom, and you can see that the phase angle also steadily drops from 0 degrees to 90, minus 90 in this case generally, when you are approaching omega c, the corner frequency. Okay, and similarly you can track the other three and try to understand. The next one is pretty easy, the high pass. What does the high pass do? It only allows high frequencies. So the low frequencies are stopped, the high frequencies are allowed to come to the output. So the gain is 1 on the high but not on the low. Now again there is a phase angle plot, and the phase angle plot is heading towards 0, beginning at some value theta, which is not necessarily 90, it depends on the circuit, but it is going towards 0. Okay, just remember that. Next we come to these two filters. So you can consider the low pass and the high pass to be of a certain type, and the next two, the band pass and the band stop, to be of a certain type. Okay. Now to define the band stop and the band pass, we have more than just one frequency, cutoff frequency to worry about. We have two now, and you can see why the two exist. Okay. So we'll talk more about all this. I just wanted to introduce you to the ideas. So I'm going to move on to slide 5. Okay. So few more things getting added. The top diagram is the low pass filter, and the bottom diagram, bottom right, is the high pass filter again. Now on the left side we show the fact that at the cutoff frequency omega c, omega is in radians, and we pick a certain value of omega c. Omega c, what is its property? Its property is that the magnitude of the transfer function at that frequency is exactly 1 by root 2 of the maximum. So if the maximum is 1, then 1 by root 2 gives you 0.7. So 70% of the maximum is what the gain, the magnitude of the transfer function between the input and the output, the transfer function of the filter circuit, the magnitude of its transfer function drops to 70% of the highest value at the corner frequency. Okay. Now if you did the same magnitude calculation in terms of power and not just voltage or current, then it actually drops by 2. So 50% of the power on the output is reached at the corner frequency or the cutoff frequency. Okay. So we'll explore that a little more, but remember that is the original definition. Now the same thing, you come to the high pass filter, it's the opposite. At omega c, the magnitude of the transfer function is 70% of the highest. If the highest is 1, then it's 0.707. Okay. Also, one other thing to show in this drawings, and remember we are still in preliminary, so we'll get into the real stuff in a bit. But the other important thing to notice is that both of them have a transfer function of a certain form. They are, first of all, they are single order, first order. They don't have a squared term in S, they only have an S to the first degree, and so it's a first order circuit, first order response. And one of them, the low pass, has omega c on the top by S plus omega c, and the other is S by S plus omega c. Okay. Alright, so that was some more preliminary, some more introduction to the material on slide 5. I will move to slide 6. and we take one more look at the general introduction, and then in the next slide I think I jump into actually looking at low pass filters. So in this lecture, let's cover these preliminaries. Let's also look at low pass definition and high pass definition and some theory. So that will take us to about 40-45 minutes. It's like we finish one class, then we come back and we do some problems on low pass and high pass. So that finishes one day of recording, that is today's class, and then tomorrow's class, 2 sections, I will do the same thing for band pass and band reject, have the theory, also maybe add in a little bit of active filter introduction in the theory part, and then one section devoted to problems. Okay, so that's how I planned it. I know it's going to be a little longer each session, 40-45, but this may be the best way to do it, is what I feel, so we don't lose the flow. Okay, so what is it that we are looking at on slide 6? Slide 6 are about these band filters. The low pass, low pass, high pass we just saw. The band filters. Oh, one other thing I wanted to again point out on the previous slide. Remember the difference between the ideal and the actual. The ideal, we want to show it as a neat rectangle, but in reality the real response is more like a linear, a decreasing value, slightly exponential, as you see on slide 5. Okay, so remember the difference between ideal and actual. Same thing here as we look at band pass filters, band filters in slide 6. Here we also have an ideal situation. In an ideal situation, in a perfect world, we would get this very neat response where the output is 0 up to a certain frequency, omega 1, then it goes up to the highest possible value, 1, for another number of frequencies, that band omega 1 to omega 2, and then it drops back to 0, right? That's how ideally you want to filter. But the real world, in actual circuits, you're not going to get it so neatly, but you can get pretty close by following those actual curves. Okay. Same thing for the band stop also. In a band stop, you want to reject or stop frequencies below omega 1 and above omega 2, and allow, actually that's the opposite. You want to allow everything below omega 1 and allow everything above omega 2, but stop everything between omega 1 and omega 2, right? That's the idea behind a band stop filter. So you can see the difference between the actual and the ideal. Another thing you see is that the 0.707 factor appears again, but this time it appears twice. There are two different frequencies, omega 1 and omega 2, that we have to define. In addition, we define something called the center frequency, which is omega 0. Okay, so we'll look at all this in a little bit when we come tomorrow, actually, when we do band filters. But for now, just I wanted to introduce you to some of these words and phrases and terms. So in addition to the center frequency, you have the bandwidth. It's probably a new thing that you're just being exposed to. So bandwidth is the difference between omega 2 minus omega 1. Okay. Now, one other thing you'll notice by looking at the transfer function is that the term in the denominator is a square term in S. What does that mean? That means this is a second order circuit, and you can expect that there will be more than one energy storage element. So it could be a series RLC circuit with R, L and C, or it could be a parallel RLC circuit with an R, L and a C. So that's why it appears with an S square term in the transfer function. Okay. All right, so these were the introductory slides just about the basic ideas behind filters. and so we are up to about 25 minutes. So I'm going to jump to slide 7, and we begin the section called low pass filters. Okay, so we spend some more time studying a little more detail on low pass filters, and then the next topic will be high pass filters. So let's do the theory of this in this recording. I do want to say that the textbook chapter 14 does a very good job describing and writing about all of this material that I am going to cover. In fact, what I will cover is a very quick summary. In 10 minutes, I want to give you the basic ideas behind low pass and high pass. Now, the writer in the textbook has spent much more time writing a lot of material. I do advise you to take a look, to read it through, even if you, ideally I want you to read it in the English language text, but even if you read it in the Chinese language text, that's fine. It will still benefit you quite a bit. But please do not think that all the material possible will be covered in my lecture and my topic. It's just physically impossible. It will take me 2 years to finish this course. So I can only hit upon the summary in every chapter, but there's a lot of the material has to be covered by yourself through your own efforts, and the textbook is a great place to start. If you find other stuff on the online, other research papers, etc., feel free, but at a minimum, please do read the textbook and try to understand that material also. What I'm giving you is a summary of what I read in the textbook and what I've learned over the years. Okay, all right. So with that, let's look at low pass filters one more time. So most of the material by now you have become familiar with. I gave you the definition of that 1 by root 2 term, the 0.707. 0.707 is just actually I would say the reason the 1 by root 2 came is because first the power equation came. Power at omega c is maximum power by 2. Remember, power, the definition, the log definition, and the absolute value of the voltage ratio, the two are different because power has a square term in it, right? Power is always I square R or V square by R. So twice or half the power means 1 by root 2 times any one factor, voltage or current. Okay, so that's why actually the corner frequency is also called the half power frequency. It's also called the 3 decibel frequency because 3 decibel means 1 unit or half drop, right? If you take the log of 0.5, which is half, you get 3 minus 3 decibel. Okay, so the half power comes from the fact that the voltage is dropping, the output is dropping to exactly half in power. Okay, but in terms of just voltage or current, it's not power, it's not half, it's 1 by root 2, which is 0.7. Okay. It's also called the corner frequency, it's called the breakpoint frequency. Remember when we were doing Bode plots, we talked about breakpoint frequency. So that same terminology applies here also. So those are some additional names and the reason why they have those names for this cutoff frequency. Okay. So a few more ideas related to low pass filter. Okay, and also more importantly, hey, you might say, show me a real low pass filter. You've been talking about it all this time, but what does a low pass filter look like? And here it is. Again, these are just first order equations, first order circuits with 1 L and R or 1 R and C. So you can implement a low pass circuit either way. Okay, and you will see how there's a slight opposite connection, right? If it's an LR, you're taking the output across the R. If it's an RC circuit, you're taking the output across the C. okay? And that's because of the natural behavior of the L and the C, okay? So why does an RL circuit? We won't look into too much detail like this in every case, but let's just look at a low-pass RL circuit to say why are we saying that this circuit passes lower frequencies but does not pass high frequency, okay? So what's the logic? So the logic, I've written it back there. Oh, by the way, what is a low-pass filter? Just to define it formally, a low-pass filter is designed to pass only frequencies from DC, which is zero frequency, up to the cutoff frequency of omega C. Okay, so that's the real definition. So why does the LR circuit behave as a low-pass filter? Now we know that the L has a reactance or impedance which is proportional to the voltage, right? It's j omega L. So as omega is low, as it becomes closer and closer to zero, that reactance, that ohm's value across the inductor becomes lower and lower. So it can become zero at DC. So it's just a short circuit, a straight wire. And you know this, we've already studied this, so this is not a new concept. But what happens when you have a wire and a resistance? All the voltage appears across the resistance, right? IR, right? I is the same, it's a series circuit, and IR gives you the voltage, and if R is close to zero, you're going to get no voltage there. So what this is saying then is, if there is a low frequency in the source in VI, let's say VI has some low frequencies and some high frequencies. So if there is a low frequency, then during that low frequency waveform existing, all the voltage appears across the resistor, because only for now the resistor will handle low frequency and high frequency the same way. It doesn't care, right? So the low frequency appears across it, but only the inductance says, oh, for low frequencies I'm pretty much a straight wire, I'm zero, so don't give me any voltage. So all the voltage just moves over to the output across the resistor, because we are calling the output voltage is the voltage across the resistor, right? So all the voltage is there for the low frequency. Now, let's say the frequency starts to increase. What happens to the inductive reactance? Its value goes up, right? So the value of the inductive reactance goes higher and higher at higher frequencies. And so assuming KVL applies and the voltage VI starting to get split between the inductance and the resistance, and you're only looking at what's on the resistance, right? That's your output. You slowly start to realize that as the frequency is increasing, the resistance is showing you lesser and lesser voltage, because more and more of the voltage is going to the inductance. So what you see across the resistance as the frequency increases starts to become lower and lower. So the magnitude of as the frequency increases, or the higher frequency components, very little of that strength of that, the magnitude of that appears across the resistance. All of it is across the inductance, but you're not really tapping from the inductance, so it's kind of wasted as far as you're concerned. So that's what we mean physically when we say the low frequency output appears at the low frequency input voltage components, they appear across the resistance at the output only when the frequency is low, and the high frequency components, if any, they never appear at the output. Okay, so that's how you understand the logic. Okay, you can apply the same logic to the other circuit below. You can start to apply the same logic. We will apply it to high pass filters and band pass filters. It's all the same, but the only fundamental facts to remember is that as the frequency increases, the reactance, the ohm's value across a inductor increases. As the frequency decreases, the ohms value decreases. Similarly, on a capacitor, as the frequency is lower, the capacitance offers higher resistance. Okay, so as at DC, we know the capacitance is an open circuit, nothing can flow through, so it's almost like all the voltage appears to across the capacitance. But the opposite happens, because the capacitive reactance is inversely proportional to the frequency, right? So as the frequency increases, the capacitive reactance falls. So what's happening, and you're measuring in the lower circuit, you're measuring the voltage across the capacitance this time, right? So what you'll notice is, as the frequency, at low frequencies, a lot of the voltage appears across the capacitance. But at very high frequencies, the capacitive reactance falls so much that most of the IR drop, the drop across the voltage drop, appears across the resistor. And you're not looking at the resistor in this case. You're looking at the capacitor, right, to see what the voltage is. And you'll notice that lesser and lesser of the voltage of the high frequency components, right, whatever high frequency magnitude is, that is not starting to show across the capacitance. Hence, both the upper circuit, the RL circuit, and the lower circuit, RC circuit, connected in this fashion. Remember, where you tap the output from is equally important. It's not just the R and the L connected or the R and the C connected, but it's also what you call the output terminals versus the input. Those also help you to define a low pass filter, because as you will not be surprised to see, the same circuit turned around is also behaving as a high pass circuit. Okay, so I hope you spend a little time, make sure you absolutely clearly well understand what exactly is going on in this slide number 8, with a low pass filter. Now, to the right we see some calculations, and those calculations tell you what the transfer function is for the upper case and what the transfer function is for the lower case. They are both the same in terms of omega c, and also the value of omega c depends on the values of the R and L, and you can see that in the two formulas to the right. Okay, all right, I have to move on. Let's look at slide number 9. And this is something that the textbook seems to be fond of. I've not seen it too much elsewhere else, but it is here, so let's see what he's trying to say. So what he does is, now obviously we have run this in the past too. You say you have a nice voltage, and how do I take the voltage? I have to connect a load to it, right, in parallel. But the problem is, as soon as I connect the load, now the circuit behavior changes, because the R value is now in parallel with another R, and so the effective resistance changes for the top circuit. So what happens with a new load resistor? So basically what happens is, with the load resistor, the cutoff frequency decreases, so the band becomes thinner. So you're passing fewer frequencies through the low pass band. Okay, so how does that value change? The K factor is introduced. K is the ratio of the extra load resistance divided by the total resistance, and everything changes by that factor K. Okay, and you see the same thing on the capacitive circuit. The K now appears, and the K goes to the denominator when you're calculating the omega c. Again, the textbook does a great job of showing you how these equations have been derived. Why is it that we have this omega c with load resistor as K times R by L? And the details are in the textbook. If you read it, you will understand the whole ideas, the whole concepts of filters much better, but we absolutely, we don't absolutely need to know the derivation, because we are more interested in solving some problems and preparing for exams. But the concepts here are important because they'll help you revise circuits in general. So I'll leave it up to you to take some time. But anyway, I wanted to introduce you to the fact that in these circuits, sometimes the load resistors make an impact. Okay. All right. Let's also move quickly, and in the next 5 minutes, I want to finish looking at high pass filters, just the theory, and then we'll solve the problems. So I'm going to skip past to slide 13, and slide 13 is an introduction again to high pass. All of the ideas here are similar. You'll just notice that the drawing is different. Now the drawing says nothing that is until omega c can actually go through. The lower frequencies are blocked. High frequencies are passed. High frequencies are allowed, and that's we call it a high pass filter. Okay, so I'm going to quickly go through the other slides. They are identical to what we studied for low pass, so we don't need to spend too much time. But again, you will not be surprised to see that these are first order circuits. So I'm on slide 14, and you see an RL circuit and you see a RC circuit. The only difference you'll notice is that the output now is, the way the output is taken out from the circuit is flipped compared to low pass. So now we have for the high pass, the voltage is measured across the inductance as the output, and similarly in an RC circuit, the voltage is taken out across the R, the resistance, for a high pass filter. You will notice that these are exactly opposite to what you studied in the past for low pass. And to understand how this happens, all you have to do is to see that again the inductive reactance is a function, is a directly proportional to omega, the frequency, and so if you're tapping from the inductance, only the high frequency will give you a high ohms value and hence a high IR drop or IX drop. And so as frequency increases, the importance of R starts falling and j omega L becomes more important, and so you say that high frequency signal components come out across the inductance and not across the resistance, and hence we call it the high pass RL circuit, and the same kind of explanation goes to the RC circuit below. Okay, so one more slide and I think we'll be done with this recording. I'm on slide 15 now. Yep, 15. And here we have the same introduction of the load resistor. This time the load resistor is connected to a high pass circuit to the right point, which is across the inductance on the top and across the resistance on the bottom. And the analysis again uses a K, and the K comes into all two. It comes into the transfer function, it comes into defining a new omega c. So omega c, if it originally it was 10 radians, with omega c, and let's say k is 0.5, then 0.5 times 10 is now 5. So omega c will change with the introduction of the load resistance. Okay, so that's so far what we have covered, all the theory. We began with an introduction of filter ideas in general, why we need filters, why is an AC signal complicated, how do you say a complicated signal has many frequencies in it. So all that we studied, and we slowly came to understand low pass and high pass with a load resistor and without. So I'll stop here. Next recording we will we will start looking at some problems only about these two types of filters. Okay.